So for this section, we're going to learn about oscillation. Oscillation is a repeating pattern that back and forth, and then one of the most common ways to look at it is when we deal with springs. So we're going to talk about simple harmonic motion. So let's talk about what we're going to be learning about in this chapter. We're going to be kind of adding another potential energy equation. For the most part, in terms of kinetic energy, we've learned about linear kinetic energy, which is an object's 1/2 mass times velocity squared, which is telling us the kinetic energy of an object that center mass is moving. We also learned that we also have angular kinetic energy, which is 1/2 the moment of inertia times the angular velocity squared, which can be rearranged into 1/2 the moment of inertia times the tangent velocity over the radius squared. Now, don't get tangent velocity and linear velocity mixed up. Sometimes they're equal to each other, sometimes they're not. They're only equal to each other when an object is rolling without slipping. We're going to have to add another potential energy equation. The one we're pretty much familiar with is the potential energy due to gravity, which we said was just mass times gravity times height, which we expanded into negative constant big G times m1, m2 over r. The other potential energy we're going to learn is about potential energy due to elastic things. Think of it like a rubber band. When we have a rubber band, we stretch it out. All the work we did, we can get back when we release the rubber band. So rubber bands, elastics, have potential energy. The formula for potential energy of an elastic is 1/2 kx squared, where k is the force constant of an elastic object, x is the displacement from the object's natural length, which we talked about earlier, but now we're just going to kind of deal with more problems. And even though this is considered the potential energy of a spring, this can be used for any elastic object that follows Hooke's law. Hooke's law is the one that deals with the force of a spring or any type of object that obeys Hooke's law is equal to negative kx. Fs is the force exerted by the spring. The reason it is negative because the negative spring is always going to push in the opposite direction of a displacement. For example, if you compress a spring, the displacement is negative, but that's because the spring is going to push back in the opposite direction that you're causing the displacement. So x is displacement from its natural length, not how long the spring is. The natural length of a spring is however it is at rest or normally stretched out, and then the x you actually plug in is how much you compress the spring from its natural length or how long you stretch the spring. So here we have an example. We have the force applied to a spring. So we have a spring right here at the bottom. It's its natural length. It's unstrained length right there. And when you apply a force to stretch it out, you're going to cause some kind of displacement. The force of the spring is always going to act in the opposite direction that the force is applied. The force of the spring is a restoring force. The spring wants to come back to its natural length. The applied force, then, that by definition has to equal kx, assuming the spring is at equilibrium, meaning you exerted a certain force, you're still exerting that force, but the spring doesn't stretch anymore. If that is the situation, then the force you are applying is just k times x. And we'll do a few problems dealing with that. This Hooke's law only works for ideal or linear springs. If the problem doesn't say that it doesn't obey Hooke's law, you just kind of assume it's an ideal spring. So if we look at this equation, this problem, when a tire pressure gauge is pressed against a tire valve, such as the figure here we have, the air in the tire pushes against a plunger attached to a spring. Suppose the spring constant of the spring is 320 newtons per meter, and the constant spring force constant the units are newtons per meter, and the bar indicator of the gauge extends 2 centimeters when the gauge is pressed against the tire valve. So what they pretty much told us is, in these little highlighted sections, is that the K, the constant, is 320 newtons per meter, and the displacement is 0.02 meters. We have to make sure that the displacement is in meters, so we have to convert to centimeters. And they want us to find the force. Now, they don't specifically say it, but we're going to assume that this is an ideal spring, which means it's going to be a Hooke's law, which says force is equal to kx. Once we make that assumption, then it's just pretty much plugging in. We don't have a negative number here because they're asking us what is the force applied, not the force of the spring. And technically the force applied is pushing down, so we're just calculating the magnitude anyways. We just put in our constants. We have our 320 times 0.02, and the force applied by the air pressure on the spring has to be equal to 6.4 newtons. Not bad. In another example here, this is more of a concept example. What happens when you have a certain spring made of a certain material, and it has 10 coils, and then you cut the spring into 5 coils? Does the spring constant change? Does it double? Does it half? It's kind of something to think about. It's kind of like a weird concept. Most people think like, oh, the spring is smaller, it's exerting less of a force, so it has to be 1/2. So the answer is A. But in reality, the answer is actually B. Oh, that's a little bit too bright. We'll go like that. Alright, so the way we do it is we draw a spring. I separate it into 10 coil spring, 5 of it is in red, 5 of it is in purple, and let's assume we exert some kind of force that compresses the string to only 2 meters. Now, we assume this is a massless spring. The spring is massless, so we think of it like a tension in a rope. If you look inside the rope, all the forces have to cancel out. If the forces don't cancel out, it means you're accelerating. But if it's massless, a massless object can't really accelerate if you apply a force, because when you do net force equals mass times acceleration, you get 0. So basically what that means is if it's a massless spring, all the forces inside the spring are the same. And since we're applying a force, and we're applying the force until the spring stops moving, and the spring is in equilibrium, that means there's no acceleration. So if we look at just the purple coil, the force S1 and the force applied have to be the same. So for the sake of argument, just to kind of visualize, let's assume that the amount of force needed to stretch the original 10 coils from 4 meters to 2 meters was 20 newtons. Since everything is equilibrium, the spring is no longer being compressed anymore. That means if we look at it and cut it halfway, it's pushing back with 20 newtons, which means this is 20 newtons and that's 20 newtons. So the original natural length of each half was 2 meters. When we compressed it, it all got compressed equally, so it went from 2 meters to 1 meter. So if we look at the 5 coils in red, we applied 20 newtons of force, and we compressed the spring from 2 meters to 1 meter. Now we have to think about it. Now we have 5 coils. The same force that once was able to cause a displacement of 2 meters is now only causing a displacement of 1 meter. And if F equals kx, so basically, and if we reverse it, k is equal to F over x, or k is inversely proportional to x. So if the same force only causes half the displacement, it's because the k has to have doubled. So when you take a spring and you cut it in half, or you remove 5 of the coils, you're actually increasing the k value. So now it actually takes, if you cut it in half, it takes twice as much. It takes the same force only causes half the original displacement, which means the K, the resistance to that, the spring constant, is doubled. So hopefully that makes sense. Now, simple harmonic motion occurs because that spring constant force, it's trying to return things into equilibrium. So if we imagine here that we stretch out a ball, and then we release the ball is not immediately going to go back into its equilibrium state. The spring is going to exert a force until the ball reaches its equilibrium state, and then the force is going to be stopped. But at the same time, the ball, if we have a mass attached to it, the ball has some kind of momentum. The momentum of the ball is going to keep it moving, and then the force points in the opposite direction. So the spring is going to go all the way back here, and then it's going to push the ball back, and the ball is just kind of oscillating back and forth, back and forth, back and forth. Momentum always keeping the ball from going back to its natural length. And if we actually take a piece of paper and we imagine the paper being kind of rolled up and there's like a little pen marker on it, it actually creates this little line here. This line actually represents the displacement, where the amplitude, which is the distance from its equilibrium to its maximum or its equilibrium to its minimum, is shown right here. So you see it just kind of keeps oscillating back and forth. Friction's eventually going to make it stop, but if we ignore friction, it's just going to oscillate back and forth over and over again, never going past its maximum point, never going back past its minimum point, just moving back and forth, back and forth. The oscillating region is pretty much can be measured as the wavelength of the wave created there, or you can just measure how far from before and how far over. It's oscillation region. So let's now look at some of those check your understanding questions and go over some of the concepts. Take some time, read them, and then we will discuss. Alright, so if we look at number 1, a steel ball is dropped onto a very hard floor over and over again. The ball rebounds to its original height, assuming that no energy is lost during the collision with the floor. Is the motion of the ball simple harmonic motion? Well, it kind of, like at the first glance, we kind of believe it is simple harmonic motion because we imagine the ball just kind of going up and down and up and down and up and down and up and down consistently, meaning that it is a repeating pattern. It does have a frequency, it does have a period, but it's not simple harmonic motion. Simple harmonic motion is caused by a force, usually a spring force, that is trying to restore an object to its natural position or its equilibrium position. If we think of a spring, the spring force constantly changes. It goes from positive force, meaning when the ball is bouncing up, if there was a spring, the spring would be trying to pull the ball down, and when the ball hits the ground, it's trying to pull the ball up. But the ball bouncing, the only force acting on the ball bouncing is gravity. Gravity always points down. It's not changing its magnitude, but more importantly, it's not changing its direction. So it's not it's not a simple harmonic motion. For number 2, it says the drawing shows identical springs that are attached to a box in 2 different ways. Initially, the springs are unstrained. The box is then pulled to the right and then released. In each case, the initial displacement of the box is the same. At the moment of release, which box, if either, experiences the greater net force due to the springs? So if you take a moment, kind of think about this. Which box experiences the greater net force due to the springs? Well, both boxes are going to have the same displacement to the right, which is going to cause it to be almost equally displaced to the left. And what really happens is the box is actually going to experience the same net force. If we look at the box to the right, imagine the box to the right is going to bounce back to the left. When it bounces back to the left, both springs are going to experience the same displacement as when you stretched it out. So they're going to push with the same amount of force. In the other side, once it pushes, let's say, to the left, the first spring is going to push to the right. The other spring is going to try to pull it, not push it, but it's going to pull and push with the exact same force because it's experiencing the same displacement. The K is the same. It's just pointing in the other direction, displacement, but the forces are going to be the same. So they're going to experience the same net force, just caused by different objects. For question number 3. For question number 3, they tell us we have a 0.42 kilogram box and is attached to the end of a horizontal ideal spring and rests on a frictionless surface. The block is pulled so that the spring stretches 2.1 centimeters, we're going to have to change that to meters, relative to its unstrained length. When the block is released, it moves, they're giving us acceleration. What is the spring constant? When they give us this acceleration, we can find the net force that this box is going to experience. The net force of this box is equal to its mass times acceleration. And then the thing that's providing this net force is the spring. So pretty much, since the spring is kx, we can say that this 3.78 newtons is equal to k times its displacement. And then we saw for k and k, the constant of the spring has to be 180 newtons per meter to cause that acceleration after being displaced that amount. Alright, so we're at the last question. It says 2 people pull on a horizontal spring that is attached to an immovable wall. Then they detach it from the wall and pull on opposite ends for the horizontal spring. They pull just as hard as in each case. In which situation, if either, does the spring stretch more? The spring actually stretches much more when they're working together. If we imagine a spring attached to the wall and 2 people pushing together, and we imagine it's the same string but then pushing in the opposite direction, we're made to think that, oh, since F1 and F2 are just pulling on it, they should stretch the same amount. But we're forgetting Newton's third law, equal but opposite reaction. When they're pulling this spring and they're both working in the same direction, the immovable wall, is going to push back with the same force. So it's going to cause the spring to really stretch at a much, much greater length than if they're putting in opposite direction. So it's essentially going to stretch twice as far. So it's going to stretch much, much farther when they're both pulling together, as long as it's attached to an immovable wall that's going to push back with the same force they exert. That's pretty much it. In the next video, we're going to actually do a lot more problems. We're going to do some questions, so I hope this helps.